Um, okay, so I decided to give you more focus on what you need to know for the exam. So hopefully that will help. All right. So so last time I told you we have three parts. Where this is here. Maybe I'll just continue here. So we have, for exam 2, we have it on Tuesday. We have 7 parts. There's overall 5 extra credit points, not necessarily assigned to any particular program. It's just a sum of 105 rather than 100 points. Okay, so for section E, I say this is inclusion exclusion. Um, and for strings, we had several ones like that in in the quiz for solutions, where I ask you something like, what are all the rearrangements of the word or rearrangements of the string such and such? Maybe I can be even more precise here to say rearrangements of strings. There are 2 levels to this. There, you can look at all those problems, and you're going to see that there are some where it is easier to count because the size of your sets are always the same. So all the size of A1 is the same as the size of A2 is the same as A3, and so on. And it's the same for the pairs. The size of the pair A1, A2 is the same as A1, A3, and so on. So all the pairs have the same size, and all the triples have the same size, and so it's easier to count. And then there is a second level where some pairs have some size and some pairs have other size, or the pairs may have different sizes. So that's like the second level. It makes it a little bit harder. So part A, this question has 2 parts. Part A is like the straightforward, where all the pairs have the same size, all the triples have the same size. And part B is like that extra step where your pairs might have different sizes, your triples may have different sizes, your singletons may have different sizes, but that's about it. Okay, so we can focus on the strings. The second part for section A, it's uh, when a degree sequence is when a list of degrees, when a list of numbers is the degree sequence of a graph. When when a list of numbers is the degree sequence of a graph. We did several ones like that. We have an algorithm, right? We have again, this one has 2 parts. So there is a part where and I tell you which one is which. So I give you one list of numbers and I ask you to provide a graph that has that degree sequence. So it is actually realizable as the degree sequence of a graph. And I ask you to give me a graph that has that degree sequence. And then in the other part, I give you a list of numbers and I ask you to prove or to show or to explain why it is not the degree sequence of a graph. Um, Definitely, you should definitely know the algorithm because the algorithm allows you to do both things. It gives you a list of instructions to actually construct your graph when there is one, right? You remember that algorithm? Where let me see, I should have one of those examples here. Um, what I'm talking about is. Um, oh, maybe I with you. Maybe I have it in the notes for section E. But I'm talking about that algorithm where, if I give you degrees, 5, 4, 4, 3, 3, 2, I don't know. If I give you a list of numbers and I ask you if it's the degree sequence of a graph, you can follow the algorithm that says remove the first one, subtract one from all the others. So 3, 3, 2, 2, 1, reorder and start over, right? So these ones are already ordered. And so again, remove that, subtract from the next 3 because I removed the 3. So minus 1, you get 2, 1, 1, 1, and you reorder. And you continue like that until you figure out whether this is the degree sequence of a graph or not. Now, here's the thing. If you eventually get to something that you can construct, and it doesn't matter how many steps you take, you don't need to get all the way down. So do as many steps as you want to either figure out that the degree sequence that you obtain is the degree sequence of a graph or it isn't. So for example, here I can keep going. 1, 2, so I'm subtracting 1 from each one and I get this. So I'm supposed to have 3 vertices and only 2 with degree 0, so those are isolated, and 1 with degree 1. But then where is that edge going? So this is not realizable. If this one is not realizable, then all the previous ones are not realizable. So you don't have to use the algorithm, but it's very helpful because you are just making your graph smaller and smaller and finding the answer, whether or not is the degree sequence of a graph, becomes easier and easier because you have a smaller graph every time, right? And the answer is going to be the same for the first one and for any for the first one, for the last one, for any in between. So, for example, in this case, I could have said from the very beginning, remember, there are certain things that you can check. Like here, I know that the sum of the degrees is off, or in other words, the number of odd ones, the number of odd numbers here is odd. And so I know that immediately that it fails the degree theorem. The sum of the degrees is twice the number of edges, so the sum needs to be even, and the sum of these is odd. So you don't need the algorithm. You can just say that. This is not a degree sequence of a graph because the sum of the numbers is off. It fails the degree theorem, or something to that effect. You can say it from the beginning. But even if you don't realize that that's true at the beginning, you could use the algorithm and eventually realize that this is not possible. And therefore, this is not the degree sequence of a graph. So none of the previous one is a degree sequence of a graph. So the algorithm is helpful for both things, to construct one if there is one, and also to prove that there isn't one by making your graph smaller and smaller, or your possible graph, your sequence is smaller and smaller. And so your answer either way gets easier in every step. Make sense?
When you mean by the sum is odd, like all the degrees added together, or the number of odd degrees we have?
Either way, you have two possibilities. You can do the sum of all of them. Um, must be even if it's a degree sequence of a graph. In this case, this is odd, so 5, 4, that list is not the degree sequence of a graph. And see, what happens is that this one fails it, right? But even if maybe this one doesn't fail that, but once you go 1 or 2 steps below, one of them doesn't fails this, fails, or you can use this for some of the lists that you obtain in along the way. And maybe you couldn't use it for this one. If this sum gives you even, then you don't know, your test is inconclusive, so you need to find something else. But it might happen that you cannot use that test for the first one, but you can use it for the second or the third. So that's why the algorithm might help you as well, because those little things that you can check at the beginning, and if they fail, then you can conclude there isn't one graph. But if they don't fail, then it's inconclusive. You can still check them for other stages along the algorithm, and they might fail later on. And so that's your proof that the graph doesn't exist. Uh-huh. So that's one possibility. Checking that the sum is odd implies that it's not the degree sequence of a graph. If it's even, then the test is inconclusive. Okay. This is equivalent to the number of odd elements, I guess. So, yeah, in the list is odd. Mm-hmm. So, I could also just count 1, 2, 3, 3 odd ones. It's odd. Then the list is not the degree sequence of a graph. But it's equivalent to 1. You don't need to do both, because it's doing the same thing, just in slightly different ways. Mm-hmm. Whichever you prefer. But again, if it's even, it's inconclusive. So if it's odd, you're done. But if it's even, it's inconclusive. If it's odd, you're done. But if it's even, it's inconclusive. All right? So, practice with that. You can even just write some numbers and see for yourself, just make them up and see for yourself if you can actually construct a graph or not. Okay, so part B, no problem to
Professor, I'm sorry, just quick question.
Mhm.
So if we found that the sequence seems like it could make a graph, do we need to backtrace all the way up, or the last step, and can we just show the last step? We can form a graph would be suffices to show the sequence. Is a degree sequence.
Okay, so if it's not, you can probably say it from the beginning. If you don't find a reason, if all your tests turn inconclusive, you can start the algorithm, and maybe in some stage of your algorithm you realize that one of those easy tests fails. You can simply say this one fails, therefore the original fails. This one is not the degree sequence of the graph, therefore the original is. You don't have to show anything else. If it is the degree sequence of a graph, I'm actually asking you to give me the picture of that graph, of one graph that has that degree sequence. So for that, you actually need to complete the algorithm and then go backwards, constructing your graph. I don't know if you remember that. Let me see, for example, maybe this one, let me make up another one. Let's see if this one, let's see if this one is the degree sequence of a graph. I don't know, but let's try. So I start I can check like the easy things, right? The number of odd ones is even, the sum is even, so my test is inconclusive. All my degrees, I have 1, 2, 3, 4, 5, 6 vertices. All my degrees are less than or equal to 5. That's fine. I don't have a 5 and a 0. So all those little things that we can check very easily. are okay. So I don't know. All my tests, my easy tests are inconclusive. So what I do is I try to apply the algorithm. So again, I remove that one, two, three, four, five. So I subtract one from each. That gives me 3, 3, 2, 1, 1. And then I keep going. I reorder. They're in decreasing order, so that's fine. I remove that one, two, three. So I subtract one from each one. I get 2, 1, 0, 1. And then I reorder 2, 1, 1, 0. So here I reorder at every given stage. And what I mean, any given stage is, this was my original this was my oops this was my original sequence, right? And then I apply my algorithm and I got this one. And then I apply my algorithm. I got that one, but that one is not reordered. So I can think of this as my next, the result of my next stage. For any of those sequences, if I can say, I can conclude there is or there isn't a graph with that sequence, with that degree sequence, then it applies to all my stages. Anyways, let's see. For this one, I have 4 vertices, one of degree 2, 2 of degree 1, and one of degree 0. If I can actually construct it, perfect. If it's still not small enough, just keep going. So for me right now, I say, well, this is only 4 vertices. Let me see if I can draw one like that. It's only 4 vertices. There should be one of degree 2, so I'm going to make that one degree 2. And then I need to have 1, 1, and 0. Oh, perfect. I have it. If that's still, if you still don't see it here, you can keep going. I can keep, I can continue with my algorithm. I subtract 1 from each. I get 0, 0, and 0. And definitely there is a graph with 3 vertices, so degree 0, right? And that would be that one. So if this one exists, all of them exist. I just need to, because I'm asking you that in the exam, I'm actually asking you, if I were just asking you to decide whether or not it is the degree sequence of a graph, you're done. But because I'm asking you to provide a graph with that degree sequence, then you need to go back. You need to backtrack and actually find your drawing. The way that you draw, the way that you find your drawing depends on where you start. Like if I start from that one, if I decided to stop right here and I realize that there is a graph that has that degree sequence 2, 1, 1, 0, then the way that I backtrack is as follows. You see, that one goes with this one. The number that I removed was 3 in my previous stage. So that's going to be my new vertex. This one is supposed to have degree 3. And it was joined to these 3, which became these 3 right here. You see? So this new vertex is supposed to be joined to those 3. And those 3 correspond to these numbers after I subtracted the 1.
Question?
So, yeah?
Earlier I remembered in office hours you told me the reason why you did this. So I'm wondering why isn't this one not skipped? Like the one below it.
I don't understand what you're saying.
Well, I mean, like, shouldn't this line be 3, 3, 2, 1, 2, and then you reorder?
Why 2?
Because this one I thought was supposed to be left alone, right?
No. The number 5 is the one that's telling you how many of these you're going to affect. So if my degree, probably you're referring to an example where, let's say, if I had something else like 4, I don't know, 4, 4, 4, 3, 3, 2, 2, 1, 1. If I had a longer sequence, when I remove the 4, I only affect the next 4. the others are left alone. So the 4 tells me which ones I'm subtracting, how many, and which ones I'm subtracting from. So I only subtract from the first 4 in this case, and I leave the others alone. You see?
Okay.
So it's not that the last one is always left alone. No. The number that you're removing tells you which ones are affected, all others are left alone. In this particular case, in my original example, I'm actually affecting every single one because there is exactly 5, right? If I didn't have enough, let's say that I'm removing the 5, but I only have, like, for example, if I had the 5, but I only had 4 for 3, let's say that was it, right? So I'm supposed to remove this one, and I'm supposed to affect 5 of them, but I don't have enough, you see? That means that my sequence is not the degree sequence of a graph.
Okay.
Mm-hmm.
And why the oh wait a minute, never mind.
Makes sense? So yeah. Okay, so how do you recover the graph? So, you apply the algorithm, you get to eventually something that you can easily say there is a graph or there isn't, right? And then the answer is the same for all the stages. If there is a graph, like in this case, there was a graph, or if you decided to stop here, there is a graph, how do you recover it? Well, I'm going to backtrack. So this is the graph that goes with this one, right? And so what I do is I see how I got this sequence was by removing a 3. So that's going to be my new vertex. You see, this 3 is going to be that vertex. It needs to have degree 3. I see which other numbers were affected by these 3, meaning from which ones I subtracted from. I'm subtracting from these 3, which became these ones, right? So I'm actually looking at that 3, and I'm looking at these ones because those were the ones that were changed. Okay? And so that means that these 3 is adjacent, or so that new vertex is adjacent to vertices in my previous stage with degrees 2, 1, and 0. Okay? So I need to join this one to a 2. I need to join it to a 1. And it doesn't matter which, just to any one, any vertex that was degree 1 in my previous stage, and to a vertex of degree 0. Make sense? And so now my degrees changed, right? Because, this one had degree 2, but now that I added this edge, now this one becomes degree 3. So I can recalculate my degrees. And that's still a 1. That one didn't change. This one didn't change. Mm-hmm. But the others changed once I added my new edges. And then I keep backtracking. So, if there's too many annotations in your drawing, then, just repeat your graph. So the graph that goes with this one, with this list, is the graph that goes with this list now is this one, right? Mm-hmm. So instead of maybe crossing out, maybe you want to repeat your drawing so it's a little bit cleaner. You could keep going in the same drawing, but sometimes it's overwhelming. So you can just repeat the drawing. So here you have your drawing, compute the degrees. Yeah. And then backtrack. So in my previous stage, I removed the 5, right? So that means that I'm going to have a new vertex that will have new degree 5. Now this is going to be degree 5. And it needs to be joined to whatever was affected, right? So all of these were affected, and what I received was all of this. So it needs to be joined to, whatever was changed. So it needs to be joined to all of those. So it needs to be joined to a 3, to a 3, to a 2, to a 1, and to a 1 in the previous stage. So it needs to be joined to a 3, to another 3, to a 2, to a 1, and to another 1. That's your graph, because we already got all the way up, right? So you see, it seems like very convenient to just keep going forever until I have like almost only zeros, because that is very easy to see if you can make it, right? But if you already know that there is a graph, and in the exam I'm telling you when there is one and when there isn't one, if you already know that there is one, it's actually better not to get that far, because then I have to backtrack more times, and backtracking is not as easy, So in that sense, it's better to stop as soon as you realize that there is a graph that goes with your sequence, so that your backtracking process is not that long. What I'm saying in this particular case is better to start from this one than to start from that one, because this involves another backtracking stage, which might take, to me, those are a little more confusing. But whatever you want to do, you could also get started from this one if you want, and it's going to be the same kind of thing. If I start with that one, I can, I have degree 0 for all of them. And then if I want to backtrack, that's the one that I removed. These are the ones that I affected, which actually became zeros. So the new vertex is going to have degree 2. The new vertex will have degree 2, and it needs to be joined to 2 zeros. So it needs to be joined to 2 zeros. This one and that one. It doesn't matter which zeros. And that graph is equivalent to the black graph that I had here. You see? So, you can stop whenever you want. My advice is that if you identify a graph earlier in the game, just use that one and then backtrack from there. Okay? Okay. All right. So, any more questions on this before I go to the third problem in the exam?
So for this part, we're either going to be given a sequence and we just say if we can or cannot graph it, or you might give a sequence that is able to graph and we have to show the graph.
Yeah, so it has 2 parts. One of the parts I said, prove that the following sequence is not the degree sequence of a graph. So that one requires some argument. So it will be, I guess, closer to something like this where there isn't. And then the other part, I said, use the algorithm, this algorithm, use the degree sequence algorithm to provide a graph with the following degree sequence. So that will be more like this one. So it's very specific. I'm actually telling you already if the sequence I'm giving you is or isn't. I'm already telling you that. For the one that is, you need to do work like this, and I need to see your work. Because I'm checking that you know the algorithm. So even if you're lucky and you can get the graph from the beginning, then I need to know what you did. For the one where you need to prove that there isn't one, it could be a combination of the algorithm, and then maybe at some stage you realize that you cannot really construct the graph. That will be it. In that one, you don't need to backtrack. You can, from the beginning, like in this one, realize that there isn't one because of some reason like this, or you can start the algorithm and for a certain stage realize that you cannot construct that. Just say why you cannot construct that. That's it. No backtracking. Okay?
Thank you.
All right. So for problem 3 in the exam, that's the isomorphisms and bipartite graphs section. So for that, you have 3 parts. One of them is give an isomorphism. So I give you the 2 graphs. I'm already telling you that they are isomorphic. You have to actually give me the isomorphism, providing the isomorphism. So you need to give me that, the labeling. And as I explained last time, I actually give you labels for the first graph, and you have to decide how to, like, which vertex on the other graph gets which of those exact labels, all right? For the second part and the third part, I'm giving you graphs that are not isomorphic. So not isomorphic. For both parts, it's the same. But in one of them, I don't remember which one's which, but so I'm not sure if B and C are reversed, okay? So read the exam carefully. But one of them is using complements. So complementary graphs. And the other one is using bipartite graphs, by showing one graph is bipartite and the other one isn't. All right. Okay. So remember that you only have 75 minutes of the period. What I'll do is, as last time, the exam will open 10 minutes before the class starts so that you can print it or download it, whatever let's say 5 minutes before the class starts. 5 minutes before the class starts, the file will be open in Canvas so you can download it, print it. I had several people, not several, but a few people who had problems downloading fast. So what I will also do is I will project the short version with no spaces of the exam in Zoom so that you can see it right away after we start the session. And, if it's taking time to download, at least you have the visual in front of you. All right. Same rules as last time. Please connect to Zoom in case there are any clarifications, any questions. Ask all your questions on the chat, private messages, because sometimes, part of your question contains part of the answer and, you don't want to advertise that. And also, you don't want to interrupt the rest of the class. So do not use your microphones. Please be nice to other people. Use the chat. Send me private messages on the chat to avoid giving anything away. And other than that, when you're done with your exam, you can feel free to disconnect. In fact, you can disconnect at any time, but then if there are clarifications, you won't get them. Mm-hmm. You'll have 15 minutes after class to upload. Right. Any questions?
Professor, in the chat, someone asked if we can go over the section E, the rearrangement of the strings.
Rearrangements of
some problems that we're kind of expected to see.
Well, I gave already a lot away, right? So what I will do is go to, I mean, we can definitely go over that, but what I'm saying is that, the type of problem of what to expect is that strings, rearrangements of strings. Let me go to the problems in for quiz 4 to show you exactly what I mean by rearrangements of the strings. Here, oh, perfect. So this one, for example, rearrangements of 111, 222, 333. So very important for the inclusion exclusion problems. Very, very important. You need to let me know. You need to let me know what are your A's. If you don't let me know, then I don't know what you're counting. Then I don't know what this is. And many times there are different ways to solve the problem. So, I need to know what your sets are. Here I define it like this: AI, rearrangements, blah, blah, containing III, all of this. I could have, you don't need to use shortcuts. You can say, I'm going to define A111, A222, or A and A333 as the rearrangements that contain the sequence 111, the sequence 222, the sequence 323. You could say that. Or maybe you're using some other sets. So that's what I need to know. Maybe you want to just label them A1, A2, A3. That's fine, but let me know what you're using, what your sets are. Make sense? So that's very important. What's you? What are your sets? And then the computations. If you just give me the computations, I don't know what you're counting. So it's very important. Now, in this one, remember that usually your sets represent what you want to avoid. So that's kind of the general rule. So your sets somehow should represent what you want to avoid. In this one, so you have rearrangements of these words that contain no three consecutive equal digits. This is what you want to avoid, having three consecutive equal digits. That's why I'm defining the sets A111 as the rearrangements that have three consecutive ones. Rearrangements that have three consecutive ones. So the subsequence 111. And then the same for the 222 and the same for the 333. Okay? So once you have your sets, you can apply the inclusion exclusion principle. And to do that, you need to figure out what are these S0, S1, S2, S3. You also need to include in your solution is usually the elements, whatever you're counting. So because it's going to be rearrangements of strings are going to be all the rearrangements with no extra conditions, So here I just have all the rearrangements, no other conditions. The AIs are the ones that usually the ones that you want to avoid. So are defined by the conditions that you want to avoid. So there you go. And then here, where the S1, and you can add those details if you want. Your S1 is the cardinality of A1 plus X, the cardinality of A2 plus the cardinality of A3. The S2 is the cardinality of the intersections, which if you follow the notation used in the book, you don't need to write the intersection symbol. So, in the book, they would just write A1, A2, A1, A3, A1, this 2, 3. Okay, so this is what you need to find. And this is where you need to explain how you are counting. So A3 is the triple intersection. And because here I only have 3 sets and I'm actually using those, that's where I stop. If I had 4 sets, I need to go to all the triple intersections. There's going to be 4 of them, and then all the quadruple intersections. Okay? So I need to count these. And what I was saying when I talk about what to expect in the test is that there are problems where all your pairs, let's say, all your intersections by all double intersections, so like these ones, have the same size. This is the case here. You see, when I count as 1, I'm actually multiplying times 3 because there are 3 here times 3 because I have 3 terms, A1, A2, and A3. And they all happen to have the same size. And so I just need to figure out how many elements each one has. But they all are the same size. That's why this is just 3 times that. And I need to explain how to count these. So for example, here I'm saying if I were counting A1, I'm counting rearrangements of 1, 1, 2, 2, 2, 3, 3, where all the ones are together so I can glue them. And now I actually have 7 symbols, right? If I glue those together, I have 7 symbols. And so the number of rearrangements is 7 symbols, but I have 3 2s and 3 3s. So, these are repeating, 3 of them and 3 of them. That's why I'm dividing by the 3 factorial, 3 factorial. But the count will be the same if I do the cardinality of A2. Now I have 1, 1, 1, 2, 2, 2, 3, 3, 3. But now I glued these ones. But I still have 7 symbols, and I still have 2 symbols that repeat 3 times, right? So the counting is going to be the same, 7 factorial with 3 factorial with 3 factorial, even though I'm counting a difference, the number of elements in a different set. And same thing, if I do A3, I'm going to have 1, 1, 1, 2, 2, 2, 3, 3, 3. I'm counting the ones that have the 3 3s together. I still have 7 symbols now because I'm making the 3, 3, 3 like a single symbol that I'm going to shuffle around. And I still have 3 here that are repeating, 3 here that are repeating. So my counting is still 7 factorial over 3 factorial times 3 factorial. I have 3 terms. So all together gives me, S1 equals 3 because there are 3 terms times 7 factorial over 3 factorial, 3 factorial. So this is the explanation why my S1 happens to be that.
It was if it was more than 3 terms, it would be a little more complicated, right? It would be like 4
Right.
choose 1 or something. Or
If you had 4, right. So if you have four sets A, A1, A2, A3, A4, then you will have another here, right? A4. And if they happen to be all the same counting, that would be 4 times whatever your counting was. Mm-hmm.
okay, yeah, like I meant and then it'd be 4 choose 2 because we would have to choose 2 groups basically.
Exactly. So if you had 4 sets, A1, A2, A3, A4, then those numbers will vary. So this is really like 3 choose 1, 3 choose 2, and 3 choose 0 times the counting, the cardinality. So that's kind of the easier type of problem involving the rearrangements of a string. This one is the same thing. I have 3 pairs, and I need to count how many. What's the cardinality of let's say A1. You can just do one example. When you do A1 intersection A2, you're counting rearrangements of these 9 digits where these are glued together because they need to have all the ones together, and these are glued together, all the 2s are together, but the 3s can be anywhere. And so now I have 3 of those, so that's a symbol that's repeated 3 times, but I only have 5 symbols because when I shuffle things, I need to move all the ones together, all the 2s together, right? So that gives me, these are my 5 symbols: 1, 2, 3, 4, 5. Okay, and so my counting will be 5 factorial divided by 3 factorial because there is one symbol that's repeated 3 times. And so that gives me this counting right here, right? 3 terms because I have 3 pairs. And you can see here that if instead of grouping the ones and the twos, I group the twos and the threes, or I group the ones and the threes, it's going to be the same answer. So that's why I have 3 of them times the counting, the 5 factorial times 3 factorial. So here will be the same for A1, A3, and A2, A3. Same kind of counting. It's not exactly the same, but same counting. Or maybe I should say equivalent counting, right? For the other 2 pairs. That's why, and because I have 3 pairs, I'm multiplying 3 times that. And then for the last one, I only have 1 term. So you can think about this as 1 times 3 factorial, this one, 1 times 3 factorial. And for that term, I have this 1, 1, 1, 2, 2, 2, 3, 3, 3, but I need to keep all of those together, all of those together, all of those together. I have 3 symbols and no repetitions. So that's my 3 factorial. And I only have 1 term, so 1 times 3 factorial. But you can, if you want, you can try to solve this problem. So try solving this problem for this one. 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4. Same property, with no consecutive, that contain no 3 consecutive equal digits. And that way, Sean's question, how those numbers 3, 3, and 1, number of terms change if you actually have 4 sets, because now I'm going to have like A1, A2, A3, and A4. So you can try that. Okay, so this is kind of similar. It is not going to be exactly like this, right? But this is the kind of problem where your cardinalities for all the different terms in S have the same counting. Now, let me look for one where that doesn't happen. This is another example where all the cardinalities of all the intersections by pairs or by triples are the same. You can see here, I'm counting, I have 5 sets, and I'm counting the number of triples, the number of pairs, the number of singletons, the number of quadruples, and each one has the same counting, and that's why I just multiplied them. So this is another example of that easier part. So these are rearrangement. Oh, here's one. This is also another possibility of that easier counting, same sizes for each. This one. So here, in this one, you can take a closer look later. All these solutions are in Canvas. You see how I still have 3 sets. These are 7-letter words using letters alphabet and gamma that contain at least 2 of each letter. So these are still the string problems. And so when you contain at least 2, you need to contain at least 2 of each letter. So what we want to avoid is having at most 1 of one letter. So these are my sets. But my main point here, you can take a closer look later, is that I actually do have 3, 3 choose 2, and 0. So, but let me see. This is another example where everything has the same. You see, I'm doing the pairs, I'm counting for alpha and beta, and I'm saying it's going to be the same for all of the others. Give me 1 second. Let me find one where that's not the case. Oh, here. You see, here I only have 2 sets. But when I count the cardinality of one of them and the cardinality of the other, I get different answers. I have 2 to the 7 for one of them, and I have 2 to the 7 plus 7 times 2 to the 6 for the other one. So this is an example where I get different things for the different terms in S. So that's closer to the second part of the question in the exam. Let's see, there's another. What's it, the first one? Oh, this is distributions. Yeah. And I think we did another one, maybe E45. You can take a look. You can go back to the notes that we had for inclusion exclusion. Look for all the problems that have strings and see. You can practice with those.
Professor,
Yeah.
can we go over the quiz?
Oh, sure. Yeah, let's do that. Okay. I'm going to have to put all of those notes together and I'll upload them to Canvas later today. So for the quiz, let's do that here. So in the quiz, I gave you some properties. Let's do that here. So on quiz 6, you had to find all so it was something like this: find all non-isomorphic simple graphs with, I think it was 11 vertices. 11 vertices, 18 edges, minimum degree 3, maximum degree 6, and 2 connected components. And that was it. Okay? So here, they need to have 2 connected components. So I'm going to have at least one vertex here and at least one vertex there. Okay? So I already kind of using that. At least one vertex on each side. Then I need to have a maximum degree 6. So maximum degree 6. I need to have one vertex, at least one vertex that has degree 6. So, and it needs to be in one of the components, right? So 1, 2, 3, 4, 5, and 6. So this one has degree 6. And it has to be included in some components. So there. So that is taken care of. Now, I need to have, as I said, at least one vertex here. I don't know how many. But I also need to have minimum degree 3, which means that this vertex, there's at least one here, but it cannot be by itself because it needs to have at least degree 3. Okay, so this one needs to have degree 3, minimum degree 3. This, or maybe more. 3 or degree greater than or equal to 3. Every single vertex has degree greater than or equal to 3. So I'm going to draw those 3 for now.
Question,
Yeah.
Professor? is this considered a component?
I haven't finished. I'm just, yes. So those blue circles represent my two connected components. I still haven't finished with this. Maybe there is more. Uh-huh.
Yeah,
So
I was hoping there should be more because so far most of those vertices are degree 1, and it said minimum degree 3. So
exactly. So, and maybe more vertices. So at this point, we haven't said that those are the only vertices, right? Maybe more vertices, and definitely more edges.
Professor, I have a quick question. When it says max degree 6, does that mean it must contain a vertex with degree 6, or just that it can't contain a vertex with a higher degree?
No, this means that it must contain at least one with degree 6, and all degrees are less than or equal to 6.
Got it. I was confused about that part. I thought it was. I didn't know it was required. Just that you couldn't go over it.
Oh no! It means because then the maximum degree wouldn't be unique, right? So it needs to be the largest of the degrees. And if it's the largest of the degrees, it's defined as the largest of the degrees. So if it's the largest of the degrees, it needs to happen.
Thank you.
Otherwise, it wouldn't be the largest of the degrees, right? So this, in other words, means that all degrees are less than or equal to 6, and there is at least one vertex of degree 6. And same for the minimum degree. It means that all degrees are less than or equal, greater than or equal to 3, and there is at least one vertex.
So as long as there are 11 vertices and then the min or the max doesn't matter, like the order doesn't matter?
The order of the degrees, you mean?
Yeah.
Yeah, it doesn't matter. The order of the degrees and the order of the points where they are, that doesn't matter.
Oh, okay. But we still have to take into consideration the 18 edges, right? Or no?
Yes, we haven't finished. And in fact,
it was just pretty confusing on like how to go about it.
Okay. So let's continue. So I have the two components. I need to have a vertex of degree 6 someplace. So I just put it in one of them arbitrarily. It doesn't matter. I didn't lose any generality. So here I have one. I drew the 6 edges. And then I know that there must be at least one vertex in the other components. So I added that. Because this vertex has degree at least 3, there must be at least another 3 vertices in this component, at least, right? Because I need to have those edges. Now, here's the thing. How many vertices do we have?
11.
11. And how many we have so far?
11.
11. So those are all the vertices. There isn't any more. So that actually, it needs to be those and nothing else. So that actually tells me that I need to have 4 vertices in one component and 7 in the other. This is the only way. I still need to complete it, right? But this is the only way for the components. Now, I still need to make sure that all the vertices have degree at least 3. I cannot have vertices of degree 1. Sean already said, I see lots of vertices of degree 1, so we haven't finished, right? But let's look at this one because this is the small component. All of them need to have at least degree 3. So, and the only way to do that is if I make this the complete graph. You see that those are the only ones that are, the only other possible edges are those, and those I need to have because I need to have degree 3 or more for every single vertex. So this is done. This needs K4. There's no other way. So all of these vertices are taken care of. That component is taken care of. we still need to make sure that all these vertices have degree at least 3, no more than 6. The maximum degree is taken care of because I won't be able to have vertices of degree 6 here. I don't even have 6 vertices. And here I won't be able to have vertices of degree more than 6. So that's taken care of. But this one is still, we still need to make sure that all of those have degree at least 3. Mm-hmm. And we haven't used the number of edges. So let's see how many edges we have so far. I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I have 12 edges so far. But we need 18, right? So we're missing 6. And the only vertices that we can use are these vertices. Those are the only ones that we can use. Mm-hmm. And these vertices, all of them have degree 1 so far, but they need to have degree 3. So each vertex is missing 2 edges, right? So if I were to draw the remaining 6 edges red, I need to use only these 6 vertices, and the red edges, the red graph needs to have degree 2, all of them degree 2, because I'm missing 2 for each. So the only way that I can do that is with unions of cycles. So I have 6 edges missing, and all of them must use the red vertices. Okay, those are the only ones that I can use. Everything else is taken care of. Okay, so the only possibility, and each is missing degree 2. So let me just say that then the red subgraph is a union of cycles. So 6 vertices, 6 edges, all degree 2. Degree 2 is what's missing for each one of those vertices. They already have 1 black edge, and they need to have 2 red edges. Okay, so the only possibility is to make a C6 or 2 C3s. So my only 2 graphs are, let me copy this. My only 2 graphs are that one with a C6 for the red vertices, and the other one with a C3 for the other vertices. So this or that. That's it. So this one is a C6, just the red part, and this is 2 C3s, just the red part.
I'm confused on the part when it says connected components. Are these 2 supposed to be connected, or am I overthinking this?
Okay, so a graph is connected if you can go from any vertex to any other vertex by a sequence of edges, by a path. So connected components are the largest subgraphs that are connected. So here, I cannot go from this vertex to that vertex by a path, right? I cannot go by a path from this vertex, let's say, to that vertex. So these 2 vertices are in different connected components. However, any 2 vertices from this side can be connected by a path. I can go from any vertex to any other vertex by using the edges. And I can also do that here. So this is connected. This is called a connected component because it's part of a larger graph. this is a connected component because it's connected and it's part of a larger graph. The graph itself is disconnected because I cannot go from this vertex to that vertex. So if I give you any graph, I gave you several examples before, but there are graphs that are clearly disconnected. Something like this. If this is my graph, this is disconnected. And to show that it's disconnected, I just need to indicate two vertices that are not connected by a path.
Yeah, I think that wording got me too, because I was looking for two connected graphs in the 11 vertices as opposed to two connected graphs.
Yep.
So you were looking for 22 vertices total?
Well, I wasn't sure what I was looking for because the whole thing was very confusing, but interpreting that sentence, I was looking for two connected graphs inside this weird non-isomorphic thing we were looking for.
Yes. So, and that's right, Scott. So you see, this is one of my graphs, and this is another one of my graphs. So
I get it now.
This graph has two connected components. So it is right what you were thinking. You're looking for two connected graphs in all that graph that you were looking for.
I understand.
I was looking for a connected graph. I was looking for one graph that had two components that were connected inside the one graph.
I think the confusion comes from the fact that connected in graph theory means that like everything within this region is connected. So if we say two connected regions, they're not connected to each other. Everything within each region is connected. So two connected regions means two regions, each connected to themselves, but not to each other.
I feel like it was like worded like that, I probably would have understood it better. But before that, no.
But that's a definition of a connected component, right? So a connected graph is a graph where any two vertices can be connected by a path. If a graph is disconnected, then the connected components are those two pieces that Noah is talking about, or in this case, two pieces, where it can be more than two pieces. The connected components are the pieces of the graph that are connected themselves. Let me show you the picture. Maybe perhaps is that you don't remember what we did in class for this. Let me show you the pictures that we had earlier for connectedness. So this one. So maybe that will click. Maybe that will bring something to your mind. Let me. This one. So here you go. You see, a graph itself is connected if every vertex is joined to every other vertex by a path. So this graph is connected because if you take, you can find a path, you can find a way of traversing, all the graph and visiting all the vertices. But in this one is disconnected because I can go from this vertex to that one and back and everything, but I won't be able to jump and visit the other vertices because even though there is this crossing, I'm only allowed to change edges at the vertices. So this graph is disconnected. It looks like a single piece, but it is disconnected according to our definition because there is no path that connects this vertex to that one, for example. So then the connected components are the largest pieces of your graph that are connected within themselves. So here I was showing you that you can start at one vertex and see find everything that's connected to that vertex. And so we started just kind of, I have that vertex is connected to these two. So that's part of the same component. And these vertices are connected to these two. So that's part of that component. But then that's it. You see, these vertices are connected among themselves. Those five five red vertices are connected among themselves with paths. That's one connected component, but they're disconnected from the rest of the graph. I cannot go from these 5 points to the rest of the graph. So that's my connected component. Even though it looks like a single picture, it's like having 3 pictures on top of each other.
Okay, so it's just different connected components.
Yeah, I get that now. You've got 2 connected graphs that are disconnected. And just that wording got me, and I was looking for something else, and it totally derailed everything. So
yeah, no, I get it. Let's see, for example, here I have this vertex. That vertex is connected to these 3 vertices by edges, right? So these 3, 1, 2, and 3. And then those three vertices are connected, like the first one is connected here and there, which we already had. This one is connected here and there, which we already had. And this one is connected here and there, which we already have. Which means that I won't be able to visit anything else, So those are another connected component. It doesn't matter what you do. You will always just keep jumping from green to green. I won't be able to go to another one.
So we will have 3 connected components?
This one has 3. We still have to check the last one, but it's going to look the same. This one will have 3 connected components. So I have this. I can start with one of them, draw all the edges that are attached to it, see where I can go. That means that whatever it is connected to is in the same connected component. So these 3 are in the same connected component. And then I can see where I can go from those 3. And you can see, I can repeat some of the edges that I already have. So I knew that this was connected to that already. They were already in the same connected component. This one. So I need to add that vertex to that connected component. And then from that one, I have this. And from this one, I have this. And I kind of close the loop, or, I cannot go anywhere else. I will only be able to move using those blue edges. Oops. Yeah. So that's 3 connected components, even though it looks like a single piece, and it is a single graph. It can be divided into 3 subgraphs. I like Noah calling them regions. But it's actually, the technical term is 3 subgraphs, 3 pieces, where every vertex in the piece can be connected to each other by the vertices in the same piece, in the same subgraph, in the same connected component are connected by paths, but you cannot go from one component to the other. So even though it's drawn like this, I could have separated the 3 pieces, and it's easier to understand the graph.
Okay, so this graph will have 15 vertices and I don't know how many edges. I'll have to count it, but this would be kind of similar to the problem we did on the quiz.
So this one has 18 no, 15, right? 15 vertices, 18, I think, 15 vertices, 18 edges, because there is 6 of each color.
Yeah.
3 connected components. And then what else we had? Minimum degree 2 and maximum degree 3.
So if you give us those things on the right, we can draw what was on the left, that graph.
Yeah, as one possibility, but maybe it's not all of the possibilities, right?
Okay.
We will need to sit down and check that if there are any others. But this is one possibility, yes. Mm-hmm.
Given that this problem seemed like it would take longer than 40 minutes than what we were given on the quiz, and then having to upload it taking more time, I felt like 40 minutes wasn't enough.
Yeah, same.
Yeah.
And
Not really.
the other stuff we got more than 40 minutes. The last one was like an hour more.
That's a problem that I typically have in my exam. And in my exam, I usually have, 5-6 problems, and the exam is 75 minutes. I understand that it can be complicated, but the truth of the matter is that, it doesn't really take 40 minutes. The issue is that there are some concepts that still don't sink in. I don't know. But that's okay. You're learning. Mhm. And I know, it's unfair to say, I can explain it in 5 minutes because you need to think about it. I understand. But I think it's fair to have those 40 minutes. And that also shows you, and I'm glad that they did, that, there are some concepts that are still not very clear. Good news, there's nothing like that in the exam. You still have time to familiarize with those concepts. Okay, guys, then I'll see you next time. I'll be in my office hours at 2 p.m. if you need me.
Would you post the solutions for the the worksheet that we did it yesterday, or so you know?
Yeah. I'll post the solutions because that was another thing I planned to finish today. But I'll just post the solutions to that one.
Thank you.
Okay, all right.
And the notes will be up today.
Yes. So by the time that I start my office hours, around that time, I'll try to do it right before my office hours. Hopefully, I'll have time.
Okay.
Okay. See you guys.
Thank you.